So we're going to start chapter 12 by mainly looking at some vocab as it relates to three-dimensional figures. So in chapter 11 and basically everything we've done all year, everything has been two-dimensional. It's been in the coordinate plane or something we can draw on paper. Chapter 12, we finally start to look at three-dimensional things, and today we're going to focus on polyhedrons. So a polyhedron is a solid bounded by polygons. So what that means is you have to think of every side of it or every face of it as a polygon. So that means there's no rounded edges. All the sides are closed. Mainly just no rounded edges, and it's closed. Makes up a polyhedron. So in a polyhedron, each little flat side is a face. So like if you are picturing like a dice, a face is like one of the squares. An edge is where two of the faces meet. You can kind of picture an edge as like a line. You can see me marking them here in that picture. And a vertex is where three or more edges meet, or like a corner. So that's a vertex, up here's a vertex, that's a vertex, that's a vertex. So like I said, today is going to be mainly vocab. We are going to see one formula that relates faces, edges, and vertices. We have a few different types of solids that are polyhedron and then that are not polyhedron that we're pretty familiar with. So we're going to talk a lot about prisms in this class. A prism, this is a rectangular prism. A prism has two bases and it's connected by parallelograms. For a rectangular prism, all the sides are just rectangles. That's why we're pretty familiar with them. We also have pyramids. Pyramids have one base and then a bunch of triangles that connect at one vertex on top. And a pyramid looks like a pyramid. That's what's kind of nice about it. But we can have different types of pyramids, like hexagonal pyramids and octagonal pyramids. Here's kind of your classic square pyramid that you'd picture in like Egypt. Down the road, we're going to talk more about solids that aren't polyhedrons, so like cylinders, cones, and spheres, but we're going to leave those for another lesson. So I want to take a moment to just talk about prisms and pyramids. I kind of said this already. We name our prism by what the shape of the base is. So this prism here, it consists of two pentagons connected by a bunch of parallelograms, which look like rectangles. So we call this a pentagonal prism because the base is a pentagon. We also name pyramids the same way. So if the base of a pyramid is a triangle, this would be a triangular pyramid. If we go back to the last page, this is a square pyramid because the base is a square. One important thing to note is the base is not always on bottom. So sometimes you're going to see the same picture with this like tipped over on its side. That does not mean the base is a rectangle. The base is still a pentagon. The only time the base is ever a rectangle is if you have a rectangular prism. I'm going to say that again because it's really easy to get it confused. The only time the base is ever a rectangle is if it's a rectangular prism. So let's play with this idea a little bit here. We have three different solids. We're going to say whether or not the solid is a polyhedron. If it is, we're going to name it, find the number of faces, vertices, and edges, and then also we're going to sketch the base. So a lot of steps if it is. Number one is definitely a polyhedron. This is what we call a square pyramid because the base is a square. We already talked about this one. That's why I'm going kind of fast. We already talked about this one. The base is a square, and then it has a bunch of triangles on the side connected at one vertex. So how many faces does this thing have? You're basically asking how many two-dimensional shapes make up this thing. So you have a square on bottom and then four triangles on the side. So you have 5 faces. How many vertices does it have? How many little corners? How many points does it have? 1, 2, 3, 4 on bottom and then 1 on top. We also have 5 vertices. And then finally, for edges, how many lines do we have that connect everything? So you got 4 on bottom, and then you have 4 kind of on each side of that triangle. So you have 8 edges. And then if we want to sketch the base, it's just going to be a square. Number 2, you can ask yourself if that's a polyhedron. The answer is no, and that's because you have this rounded edge. This is not a polygon, so that's not a polyhedron. Bummer. For number 3, we can tell there's triangles in this thing, but it definitely doesn't look like a pyramid. So what we have is we have two triangles that are connected by a bunch of what look like rectangles. So we call that a triangular prism. And it's obviously tipped on its side, so the triangles are kind of in the front and the back instead of the top and the bottom. But those triangles are indeed our bases. So I'm going to go down here. The base of this thing is a triangle. This is one of those cases where the base is not on bottom, but clearly you could just tip this thing up and it would look like the triangle was on bottom. Let's run through faces, vertices, and edges. How many faces does this thing have? Well, it's got one in the front, one in the back, and then three kind of around the outside. You have the rectangle here, the rectangle on the bottom, and the rectangle on the left for 5 faces. How many vertices does it have? How many corners? Well, you got 1, 2, 3, 4, 5, 6 vertices. And how many edges does it have? It's got 3 in the front, 3 in the back, and then 3 connectors. So our edges is 9. So a long time ago, there was a mathematician who looked at a bunch of these polyhedron, and he noticed a relationship between the faces, vertices, and edges of any polyhedron. He noticed that, well, if you add the faces and the vertices, you always get 2 more than the number of edges, which we see here. You get 10, which is 2 more than 8, 11, which is 2 more than 9. So that mathematician came up with his own theorem, and he proved that, and it still holds true today. That mathematician is probably one of the most famous mathematicians of all time. His name is Leonhard Euler. You don't pronounce this name as Euler. It's Euler, like someone who like oils something, or like a tin man, like oil can. Euler. So anyway, Euler's theorem says the number of faces plus the number of vertices is equal to the number of edges plus 2. So what we can do with that is we can say that if a solid has 8 faces and 12 edges, we can determine how many vertices it has, even if we didn't have a picture. So using this formula, f plus v, we'll do 8 plus v, which is what we're solving for, is equal to 12 plus 2. 8 plus v is equal to 14, so v is equal to 6. And in this case, we have a picture, and you can clearly see 1, 2, 3, 4 vertices, and then 1 on top, 1 on bottom to make 6. Last thing we're going to talk about in this lesson is kind of prepping for what we're going to do next. Any type of 3-dimensional figure can be broken down into what we call its net, which is basically a 2-dimensional picture of that. So some of you have maybe made like dice out of paper before by making like one of those crosses that looks kind of like this, and then folding it here and here and there and there and there, and kind of folding all these pieces up into a cube. You can do that for any type of prism or pyramid. So you can see that here with this rectangular prism. We're going to use this strategy in a later lesson to find surface area. This would be a triangular prism, because if you folded all these sides up, you would get a picture that looks actually kind of similar to this one. This would be a pentagonal prism. You'll see clearly that you have 2 pentagon bases connected by a bunch of rectangles. That's a pentagonal prism. This would be a triangular pyramid if you were to fold up all of these corners. And this would be our classic square pyramid if we were to fold up all of those triangles and connect them at one point. So this is more just highlighting what we're going to be doing in a future lesson to determine surface area. So I just kind of wanted to put that idea in your head. But that's it for 12.1.